Okay.
Okay. Nice.
So, yeah. So here we are with the communications podcast. Uh,
Hello,
yeah. So, Shri, do you want to introduce yourself?
hello all. My name is Shreya Mandala. I am the communications lead, as in regards to, I guess, April 1st, 2023.
Oh wait,
Yeah,
I forgot we just handed off titles, but okay, yeah, you're basically
yeah,
you're
yeah. Um, I guess this is probably going to be more directed for James or for anybody else who will be future communications lead. Yeah.
You sound just as dead as you did at the beginning of the semester. And all right,
Greetings.
all right. Okay, yeah. So that's Shri. The next lead is going to be James, who will probably watch this video first, uh, or be among the first. Okay, yeah. So can you give it like, all right? So just give us like a quick overview of, like what communications lead has been like for you. What
Um,
what the importance of the sub team is, etc.
okay, so I'm gonna write it out in text. So, so communications lead, often you have to deal with a lot of responsibilities, right? So, obviously the biggest one associated with communications is the fact that you have to handle the link budget. Now, the link budget is just this budget to describe the viability of your connection between your Keep satellite and your ground station. Furthermore, another aspect that you will have to consider, no matter what kind of communication system you do, is FCC licensing. Because what happens is, in fact, in order to even be approved for any communications in space, you are going to have to operate through an experimental licensing band accordingly. And then also you have to make sure that you have a ground station. So that just means checking for your ground station services / building your own. And obviously, this is more oriented towards someone who has experience in electrical engineering specifically, or RF engineering, either of those two. Because what happens is generally a lot of what you're going to be dealing with is going to be focused on radio frequencies or electrical circuits accordingly. However, personally, from my experience, I have none in these fields. So, so I had to learn almost all of it, pretty much by textbooks or research papers. And granted, I'm still am like relatively a novice in comparison to someone who's in the field for like 20 years.
That's fair.
20 to 50 years,
Uh,
because purely it changes over time accordingly. And a lot of what you actually are going to see in communications is going to be of what is probably currently 10 years ago, because that is how the communications field works in general.
damn.
Okay. Yeah.
Discouraging every communication lead that comes after you. I like it.
I don't think it's discouraging. I think it's like you're working on what is considered modern tech.
That
Like
is true.
like think of it like in terms of like 5G and 6G stuff, right?
6G.
Like it's going to be stuff that is, and by the time this is 2023, technically 6G hasn't come out yet. So technically it's stuff that you'll never that you'll consider in the future.
Yeah.
You are doing probably work that will be obviously common later on, but for now you are just one of the sole people that are actually exploring it.
I don't think it's discouraging either, because you're basically saying that like next to lead, you might not know what's going on, but like no one does.
Yeah.
Not discouraging. You learn everything yourself. You learn everything for the first time, no matter what, no matter if you know it or not.
I had a feeling this type of conversation would come up, so I edited the description of the podcast videos, or like the playlist, and I said, by the way, we're not experts, so don't trust everything we say.
Oh yeah, but in all fairness, it is not too bad. Overall, obviously, when I was starting out, my lead Nick Florio um was just handling electrical stuff. So he used to be the old lead, and even then, he did not know anything about S band. Nothing about S band.
If he did, he didn't tell you.
Oh no, he definitely did not know because I asked him.
Oh.
So nothing about S band. So guess who had to learn S band?
Real mystery.
Guess who had to learn S band?
Actually, wait. Give a quick overview of. I guess
This
like first go
guy.
through bands. So first describe like how what a band is in communication systems, and then go through
Okay,
like what.
okay, I
Yeah.
can do that. I can do that. Let's erase these. This guy. So basically, what's happening is bands are just usually a range of frequencies that you have. Obviously, when we're considering these range of frequencies, you want to operate in frequencies that you're permissible to operate in. So this is just what's allowed for like common communications. A notable example is for internet protocol, usually 5 gigahertz or 2.45 gigahertz are common frequencies that you utilize for that protocol system. Obviously, depending on what kind of systems you need, the most common ones are like radio stations. Radio stations operate in the megahertz to the kilohertz. And because of that, there's obviously a lot of protocols that are implemented along each of the lines of frequency accordingly. And then you have to basically make sure that it's viable for FCC licensing and also viable that no one else is using those communication frequencies. Otherwise, you get something called interference, where basically both those signals are trying to communicate on the same frequency and they basically interfere with each other. Think of playing a really loud song, but then your roommate basically also plays a different song, and so it just mutters up all the words, so neither of you can actually listen. So, in a similar context, that is how usually radio frequencies and bands work. Now, in regards to S band, and S band is in reference to usually, it's like usually 2 to 4 gigahertz range. So that means just generally any signals that are from 2 to 4 gigahertz fall under the S band. Um, in regards to what commonly is utilized for satellite radio operations, it usually follows UHF and VHF. UHF and VHF stand for ultra high frequency and very high frequency because they don't have really good naming terminology. But UHF basically stand for comes around usually 300 and like 70 megahertz to 512 megahertz. While VHF usually falls along the lines of like 108 megahertz to like 216 megahertz. Obviously there's different purposes for each of them, but what happens is commonly for most satellite communication systems, UHF is going to be roughly around 435 megahertz and VHF is going to be around roughly 135 megahertz. However, for S band, S band's a bit different because obviously it's operating in the gigahertz. What you have to consider along the lines of that general frequency is both radio waves, internet waves, and potentially other satellite communication systems, because they all operate relatively in the range of 2 to 4 gigahertz accordingly. And so because of that, um, the FCC fortunately has licensed a specific band for S band licensing, especially for space research operations. Space research operations fall between 2,200 to 2,290 gigahertz, roughly. So anything along that range is basically conclusively good for space operations.
So there's like a
Now,
dedicated amount or like a
there,
dedicated range for.
there is a dedicated range for space communication systems. However, just because there is a dedicated range doesn't necessarily mean that there's other areas where you can also communicate in S-band, because you can still get experimental licensing, and if the government deems it useful enough, they will oftentimes serve the benefit of the public good and then reallocate licenses or bans accordingly. So just don't think that this is just a limited range, but it's just a range that is common for space research accordingly.
Nice. Good to know that there is in fact a range out there specifically designed for missions like ours.
Yes. Obviously, I don't know how far you guys want me to go with this, but like, there's obviously X band as well, and then there's C band, and then there's L band. All these bands are just other different operations that sometimes they do space communications for, but in regards to what we have to deal with in terms of nano satellite communication, generally you can safely assume that S band is the threshold, and if not, most go only up to X band systems. Otherwise, if you don't, then like, yeah,
You get in trouble.
yeah, no, you pretty much get in trouble.
I
But
believe this is
yeah,
accurate, right? This is the distribution.
that is accurate. Now, basically, just to point out, the reason why there's a difference between C band and L band right now is C band actually deals more with actual aviation systems, so like airplanes and all, and then L band is more used for, I think, commonly submarines and only like Navy
I found this.
systems. Yeah, no, but like no, like there's like they give a specific registration. It's not just the chart. The chart's like not going to be entirely useful. Like
I see.
no, they specifically, there's a specific document for the FCC that they go over what every single range is used for specifically.
Okay. And that document can be found where?
On the FCC. It's on the, I think it's FCC licensing sheet.
Okay.
You can look up all the different like not FCC licensing. It's like FCC spectrum range, or not range. It's not the table. It's like a specific sheet that they have that like literally goes over every single one. Let's see if I can find it. Let's see if I can
It's fine
find
if we can't find it right now, but
I found it. Okay, I found it.
Well,
So basically, let me just,
send it in the voice chat and I'll just pull it up.
don't worry, I'll send it through here. Okay, so there you go. That you literally
No,
deleted
my
it.
bad.
You literally deleted it. So that is the actual table of systems. I will also send it in chat as well.
Yeah.
And this goes over all the available spectrum and what all the actual allocation goes to specifically. Just to remember, this is going through there's the international table and the United States table. As good reference, if you ever see something that's labeled in regions, make sure that it is labeled in region 2, because that fits into the United States frequencies and
Okay.
laws.
Yeah, so there's the international table and the United States table.
United States table is just there for simplicity, but you can technically look at region 2, or the second box on the international table side, and then that usually corresponds to the actual American system.
Okay. All right, yeah, that's really good to know.
Um,
All right. Okay, yeah, so that goes through S-band, a quick overview of it, and then planning around it, and a little bit of the FCC licensing that has to go into it. So, next up, all right, describe the communication subsystem itself, like the hardware that it has, if there's any software running on it. Just a quick overview of the like actual subsystem within the satellite.
So there's obviously the big one, the transceiver. That transceiver is the biggest one on the actual satellite. Then there's the antenna. The antenna is very hard to actually indicate which one you need. Obviously, the one that we're using for S band is an S band patch antenna.
Okay.
So there's actually different purposes for the antennas. So obviously, if you use directional antennas, they actually have a significantly higher gain, which allows you to transmit more information in a one directional area. And by one directional, I mean just like in like basically a single line at that moment. There's obviously different monopoles and dipole antennas as well that you can use. But usually the design for those consider more an omnidirectional system. So when I mean omnidirectional, I mean like it basically tries to emit the entire wave of information in all 360 degrees, as opposed to a certain confined area of like 30 degrees or so. Um, Depending on your purpose, you don't need to know too much about the antennas other than like the one you're trying to use for your system. For our system, we plan on using an S-band patch antenna because we want to make sure that we have both a high gain and also a relatively high data rate as well. And that is only really achieved through like these directional antennas because they allow for just handling more power accordingly. Um, and then also there's other things you have to consider. Some of them are specifically designed for left circular polarization, right hand circular polarization, linear polarization. Um, Basically, that just means how your wave looks. I see Banav's drawing it. Uh, so depending on how your wave looks in terms of its actual emission, that can actually influence how much data you receive accordingly. Usually, you want to have a circular polarization because that means you can actually transmit more information in the same amount of power because it's going in a circular direction and that circular direction actually allows it to give it a distinctive time sequence accordingly. Um, for linear polarization, that is much um, easier to do in terms of transmission, but it comes with some issues accordingly. The linear polarization, what happens is you can only receive it from generally one slit frame. So you basically have to make sure that your accuracy with lining up the wave is almost perfect. Otherwise, inherently, you're going to capture barely little to probably 0% of the information in the wave. That's why one of the benefits of using a circular polarization is even if there's some potential error with the circular polarization, you could still capture a lot of information because obviously a circle covers more general, I guess, perimeter than that of a linear system.
Just to clarify and make sure I'm getting the picture right. So for a linear polarization, your antenna would have to be oriented like vertically along with the wave that's coming in.
Yes.
And if you were say like 90 degrees off, then this antenna would receive zero signal.
Pretty much.
However, if you had a circular polarization signal, then your antenna could be anywhere and it'll receive, I don't want to say the same, but roughly the same amount.
Well, that's under the presumption, once again, I should clarify that your ground station antenna, whatever antenna you're receiving with, is also a circle as well. But inherently, because obviously you're trying to match up a circle with a circle, it doesn't matter how the circle is oriented, it will still capture all the information accordingly, even if the circle is slightly turned.
Right, so it's independent of this angle. Okay,
Yeah.
I see. And most ground stations are like this type where they have like a
Most
giant.
ground stations are circularly polarized. Now, the thing is, if you do use a linear receiver on a circularly polarized system, inherently that reduces your signal by half or -3 decibels.
-3 decibels. Okay, good to know. People with an actual background who understand decibels more than I do will know what that means. I hate the concept of decibels.
Well, you just assume half power.
Yeah, half power.
So generally that's the antenna components. The transceiver, there's a lot to you can cover with that. So obviously there's the concept of full duplex operations where you want to make sure that your system's able to transmit and receive at the same time. Or you can do half duplex operations where it can receive, and then it can also transmit. Um, However, there's always some implementation some people do. If they just need to transmit the data, they just transmit accordingly. So that's just they just need a transmitter. They don't ever need to make sure that they send their ground station data up to the satellite. For our operations, though, we need a receiver because we want to upload our algorithms as well, for further like control experimentation accordingly.
Yeah.
So
So we have data being sent down, and we at the same time we will also be sending like um, commands and algorithms up. So we want to be able to do both. The full.
yeah. Now, in regards to transceivers, obviously they're going to be, in terms of relative power, the most expensive operation other than the ADCS, because generally to transmit a signal you need to send power, and for communication systems they generally require a lot more power to bypass atmospheric losses, polarization losses, and also potentially pointing losses accordingly. Uh, so because of that, they usually consume relatively the most amount of power. So it's good to make sure how much power consumption they have in the system. Another thing about transceivers is you can either develop your own modulation schemes, or you can basically come up with just the available ones that are given to you accordingly. Now, there's obviously a lot of modulation schemes. I cannot really go into all the specifics or nitty gritty, but
Can you
uh,
explain what modulation is first?
oh, okay. So I can do that. So modulation basically revolves around, you have this electric wave. Now this wave basically inherently also does not contain any information on it. However, we want to make sure that our signal actually sends data across, right? So what we do is we combine the data, which is represented in zeros and ones, obviously from a computer, and we combine it with this electrical signal, this random carrier wave, and then we modulate it. So that means either like changing the frequency, changing the amplitude accordingly, and then that produces a wave that contains data. Obviously, there are much more complicated ones. There's binary phase shift keying, which is very popular. I know the one that many people want to use now is QPS, and QPS is actually based on, funny enough, a three-dimensional view of your signal, because based on like where it's actually positioned in like rotation of a circle, your values of zeros and ones can change accordingly. So I guess, wait, can I add pictures?
Um, Send me the picture, and I'll add it because you have to download the image first. So I'll do it.
Oh, you have to actually download images.
Yeah, you have to. There's this thing called Add
Bro,
Picture, but you have to download it.
what
Just
is
send it to me. Just
this?
send it to me. I'll download it. I'll download
What is this?
it. It's okay.
Okay, let's see if this works. Wait, no, wait, hold up. I can't get this to work. Okay. So I do want to explain QPSK at least, because QPSK, quadrature phase shift keying is like relatively important, especially for like a communication system like S-band. So I can't really. So okay, I guess I could just say, obviously imagine a circle, right? You got the circle. You have different points on the circle in terms of iteratives of pi over 4. So
Yeah.
pi over 4 is just naturally 45 degrees, right?
Are you
So,
are you looking at my stream right now or no?
oh, wait, are you?
I'm
I
pulling it up.
am. Oh, did you have QPSK up?
I
Okay.
searched up and I found the image you're talking about.
Okay. So they have 45 degrees. Now, this 45 degrees, actually, go to the first image, understanding QPSK. So these degrees actually associate with the actual representation of the signal. So based on the certain shift, you can actually represent a 0, 0, 0, 1, a 1, 0, and a 1, 1 accordingly in your wave. And then what happens is your computer actually slices these sections in the wave in order to actually determine the bits. So the way it works is based on like just the phase shift of a circle, right? it determines accordingly. Oh, these values are 0, 0, or this is 0, 1, or this is 1, 0 accordingly. And they can be commonly identified in your system no matter what, because they have each a unique shape that will constantly repeat over time with your overall signal accordingly.
Spencer, so something I remember, which Shri should confirm. I think it's computers are better at identifying changes in like the electric and magnetic fields as opposed to the raw value of the field itself because that can be noisy. And so
Yes.
this sharp corner here and this discontinuity are easier to detect than something like just a continuous wave.
Yeah. And just to, I guess, clarify, how it detects. Usually computer algorithms, for communication systems use, the concept of sampling and levels. So the levels are just the general amplitude of your signal, while the sampling is how many times do you actually take that sample for. So that means just like how many parts of the signal do you actually capture? Do you capture like only just one little tiny value or one point on the wave, or do you capture multiple different points on the wave accordingly? So wait, actually, you can look up sampling and levels communication. So, like, you take different samples of your wave accordingly, and then from there, it's able to detect those changes because while they're maybe minute, it has enough levels and samples in its system that it comprehensively is an intelligible signal to a computer. And that is the same way that your phone communications used to be done. Actually, no, not used to be. That was actually the innovation of 2G voice communications.
I'm pretty sure most people don't know what 2G is, unfortunately.
2G, oh,
I think most people start with 3G as like, oh, that's a familiar term from the iPhone, but
yeah, but like
it's this
obviously,
it's this idea that was carrying or that is what defined
in
2G.
inherently, it's just that all your signals for communications are digital as of now, as of when it was analog.
Yeah.
And so the transceiver obviously does the modulation schemes and then also the decoding schemes accordingly. And overall, the transceiver basically holds almost like the main OBC of your communications, which is funny considering the fact that we also have an OBC that can also do the same thing. But even still, that is the general purpose of a transceiver.
Okay.
In regards to any other components you would need, it is important to consider wiring inside your communication system because one of the most common things that can happen is one, you could have impedance where basically your wire's resistance does not match up, and that causes a phase shift in your signal accordingly, and that could potentially cause it to lose enough a lot more information. And then there's also the concept of line loss, where if there's enough resistance in your signal, that effectively reduces the amount of power that your signal receives when transmitting out.
And that's something that you would calculate in your link budget.
Yes.
All right. Let's see. So that's a quick overview of all the components. And then okay, so we
You
mentioned
want me to go over link budget?
no,
Or
not
no?
yet, not yet.
Okay.
We'll do like a quick overview. We're not gonna do like an actual full on like calculation of it. But before we get
Okay.
to that, we're gonna talk about ground station, like ground stations in terms of. So we've already discussed like FCC licensing,
Yeah.
and like allocate getting in like a frequency allocated for our mission and and all that fun stuff. But I guess the odds are that we purchase a ground station service. So can you go through like what are some considerations for that, challenges,
So
whatnot?
I think one of the most important things for a ground station service to consider is first location. And location matters because that determines your access windows. And effectively, if you have smaller access windows, you have less time to actually transmit your data. So accordingly, make sure that's the first thing that you have. Because if you know your satellite passes over one location more often, you're going to have to use that location more often to get your data. Otherwise, you're going to have to almost like cross your fingers and hope, oh yeah, I can definitely transmit all this information in like 2 minutes time. So that's the first thing. Second thing in most ground station services is ironically still licensing, because you have to deal with approval of licensing with your system, but then you also have to make sure that your system is good with their system to make sure that it doesn't interfere with any of the other systems that use their system. Did that make sense?
You said systems a lot, but I got it. It's compatibility and interference.
Yes. So that's one other thing. Now the final aspect I would really consider in the ground station service is making sure that the financial cost makes sense to you. So, roughly speaking, most ground station services offer the ability to reserve a time. However, just because you're allowed to reserve a time doesn't necessarily mean it's advantageous for you, because sometimes they charge more because they are aware that this is going to be a competitive hour. So, what you want to make sure is you maximize the amount of minutes you have. Most of the ground station services offer it in terms of minutes. So, you basically schedule a certain amount of minutes and then you use that accordingly for communications. To be aware of with the system, make sure that you actually use your minutes. I don't think wasting money is a good option no matter what.
Yeah,
um,
use your downlink
oh,
time wisely.
actually, like that is for like procuring ground station service, and like just the general overscope. Another thing you want to consider is just the specifications of your ground station. Like, obviously, you don't want a ground station that does not work optimally with whatever frequency or whatever components you have. You want to make sure that it has a substantial gain. It works with the specific polarization you set for your signal. You're able to ensure that in general, your satellite basically just works with the ground station and actually processes the information, because they also have to have decoding modulation systems on there. Otherwise, what you get is although wait, actually, you don't really need modulations on your actual ground station, but what happens is some do offer it. I would say that's probably better, because what happens is then you have to do it yourself, because what you get instead is waterfall telemetry. And waterfall telemetry is just basically a bunch of static noise to most humans, but to a computer, it apparently is perfect sense.
I think I've seen this before.
Waterfall telemetry.
This thing.
Yes. That is
Yeah.
what your signal will look like when you actually receive it from the ground station.
Yeah.
Now, I guess in regards to if you want to like pull up more information, general good waterfall telemetry. I know this will probably not be big of an issue. You want to make sure that there's not that much scatter, or basically your signal is as like clear as possible. Also want to make sure that it's pretty green, because you'll notice that your waterfall telemetry can sometimes just vary or shift off. Yeah, like you don't want to have like faint fuzzies. Those are terrible. Those are really terrible. Yeah. You want to make sure that it literally looks like a waterfall straight down.
Yeah. You said scattering. I'm assuming this is like atmospheric scattering of
So
electromagnetic radiation.
yes. So obviously you will always have some initial environmental conditions as well. Um, so when I said location, it's very important the fact that like temperature also plays a role, because based on the certain environment, it might be beneficial for communications. You want that good solid
Sunny
like
weather.
sunny weather, pretty much average temperature. You don't want it to be too hot, because obviously what happens is you can increase the noise temperature of your system, and then that will like create more noise thermal temperature, and then that can create more interference. You want it to be like a sunny day, no clouds in the sky, and
Like a
it's
cool
as
breeze.
yeah, pretty much. But you don't want the cool breeze. You just want it to be relatively mild.
Yeah.
Like you want it to be in California, but in the winter is probably like the best description. Although I don't know if California right now is a good example, considering I heard they were like dying of rainfall. But anyways, yeah.
I want to bring something up. So this is a thing I worked on way before, and I think you were here when I did it, but I stopped working on it soon after you joined.
Access windows.
Yeah, these plots that I used to make. So these were made in STK, and the idea was we would take a ground station, give it like, the parameters of like, okay, what are the accessible angles, what is its range, and then we would propagate orbits and color code them based on how much time they were able to see per day on average, right? So we would run this simulation for like a month or 6 months and then average out the total time divided by the total time in the the average access time is what we wanted. So we would take the total access time over 6 months divided by 6 months, and then we color coded it based on its needs. And so you'll have like this optimal band right here, which is this blue, and then you'll have like a little bit of green, which is like, it's there's a lot of time, but it's not like the most time. And then yeah, red and white was like no time at all, right? So if your orbit is like along the equator and your ground station is like way up here, you won't see it. So this was something that we worked on. This was the 2D version of that plot. So you can see, like, at small inclination angles up here, you barely see your ground. You don't see your ground station at all. Then you see it like a little bit, and then you have like this optimal range here, which is a function of the altitude and the angle of inclination, which are two orbit parameters. And I think this one was based on Rutgers. This is when we wanted to build our own, but we know we're not doing that anymore. But you could run the same analysis with any ground station anywhere else. That did not account for weather, by the way. We just assumed 10% error and moved on because we didn't know any better. But to whoever picks up that project after, like, that is an interesting that is an interesting addition that could be added. And the code is somewhere on my GitHub, but I don't know. I'll share with you, Spencer.
I'll keep that in mind. That seems interesting.
Mm-hmm. Yeah, it's not. If the manpower is available, it's an interesting project. But for us right now, it wasn't that important. We don't really need to know any more than like what orbits are okay, and that was mostly like a thermal thing. But a communications perspective is important here because the ground station does determine how much access time we have, and the amount of downlink time is in fact how much we can experiment, right? Because we can run an experiment like, we like hypothetically we could run like 2 experiments a day, or hell, we could run like 1 experiment per orbit, but we do need the access time to send all that data down in order for it to be useful. There's no point in generating data if you can't get it. Yeah. Okay. So, Shri, do you have anything else for ground station or?
So ground stations are obviously one of the biggest issues, but in regards to your actual focus, it should probably be more on the transceiver antenna until you actually complete it. What you should be still focusing on is making sure that you have a relative contact point so that you can showcase your system to them later on, and then make sure once again to have the licensing available, because what happens is most people have completed systems, but they just can never actually do anything with them because they just need actual approval for that.
Oh yeah, we had this discussion with UNP. Do you remember when we had lunch with them during the video?
Yeah.
Yeah. So
Yes.
are we allowed to share that? I feel like we should be.
Yeah.
Yeah, it
It was
wasn't.
not anything. No, I don't think it was anything secretive.
Yes.
Personally.
So the program that we're under, the University Nano Satellite program, they made us. They had a mission plan, which was how fast can we go from concept design to launching a satellite, and the satellite's name was U2U, which stood for unnamed 2U, right? It was just a 2U satellite that was just meant to see like, okay, how fast can we get this thing into space? And
It took them 1 month to make, right?
yeah, it was something like, it was like on the order of months or weeks to make. However, they didn't get the licensing, so they couldn't launch it. Yeah, so they couldn't launch it. And so I think the guy mentioned like they just had to leave it in like some shelf in their basement because what else can they do?
I mean, yeah. I mean, I think that's a good example. It goes to show that no matter like what you actually do, mind you, these are like the actual professionals who are supposed to be launching cube satellites,
Yeah.
and even then, they also have issues with licensing.
Mm-hmm. Yeah, so for licensing, they told us this, and so now we're gonna tell everyone, which is get licensing done as soon as possible. Always have someone working towards it, because if your mission gets approved and you don't have licensing, you will not fly. You will not be allowed on that rocket. A bit unfortunate, but oh well. Okay, yeah, so that's all for licensing and ground stations. Now, okay, let's go through the link budget. How are we doing on time? We're at 40 minutes. Oh wait, we're actually doing great. Okay, yeah, so
How long are we supposed to go for?
my plan is like an hour ish. But
Okay.
like if we go a little bit above or a little below, it's no big deal. I think an hour should be plenty for like anyone understanding.
Okay.
Yeah, so we'll do like a quick overview of the link budget, and then the final thing is the phase B stuff, which is the simulated communications test.
Okay. So link budget. Link budget is probably the hardest thing I've probably ever done in this CubeSat team because it's just annoying, frankly. However, in regards to link budget, so there's different concepts.
Or
So
wait, start with like a quick overview of like what it is.
okay, quick overview is it's supposed to test for the viability of your communication system. And the way they test for this viability is by just making sure that your link between your ground station and your cube satellite is just greater than like 6 decibels. Now, this is an obscure number because technically the better it is, the stronger your signal is. But inherently speaking, it is just 6 decibels for now in terms of reference.
The noise?
No, greater. It is greater.
Okay, wait. Let's just clarify. When you say greater than 6 decibels, that means that the signal to noise ratio is greater than, or no, yeah, is greater than 10 to the power of 6. And then convert that to decibel. Oh, yeah.
Okay, so actually, like, no, technically.
No?
It's okay. Okay, let me actually just make sure before like I actually like because I do want to make sure one second about the 6 decibels part. The
Yeah.
6 decibels refers to if I believe the gain over temperature. Yeah.
You gain over temperature. So I'm assuming this is like thermal noise.
Yeah.
Okay. So, and this has to be greater than 6 dB, which is something 10 to the power of 6.
Mm-hmm.
Okay. Yeah.
Pretty much. And then yeah, no, it's honestly like the really this is hurting me now. But so the link budget, the entire purpose is you're supposed to calculate all your gains from your actual transceiver and antenna, and then minus that with all your losses, which come from the atmosphere, the circuit, the polarization, the pointing. Am I forgetting any others? I believe that is all the losses you can possibly have. So generally what happens is for atmospheric, because of rainfall and the actual layers of the atmosphere, they actually will reduce your signal by attenuating your signal, which means just basically interfering and like reducing the amplitude accordingly. In regards to the circuit losses, that is introduced electrical magnetic interference usually that basically affects the system. Oh yeah, by the way, most cube satellites, Manov, they don't actually go straight in the atmosphere. They go zigzag.
They zigzag?
Oh, they literally zigzag. they literally zigzag like that. Yeah. No, they zigzag in the layers and then they go straight down.
Oh, okay, I remember. This is like I remember now. It's like it's the physics thing with like diffraction and reflection
they zigzag.
Yeah. Okay.
Until they don't zigzag. So like
yeah. So it'll like zigzag like for every layer it'll bounce like at some stupid angle, and then like once it like gets to like the main part of the atmosphere, it's like just straight down.
Yeah.
I remember this. I remember this now.
Yeah, pretty much that entire gist. In regards to what the circuit losses, that's introduced electromagnetic interference, which basically distorts the carrier waves accordingly, or when processing the carrier waves, and that could potentially cause issues with your signal. For pointing loss refers to did your satellite point at the actual direction of your ground station. Now, this is the most common sense one because it's like if you don't point at your ground station, how does your signal get sent?
Yeah.
And vice versa.
So like there's gonna be some deviation, you could say, between your
Obviously, you want as completely dead center on as possible, especially for a directional antenna. If it's omnidirectional, and pointing loss is absolutely does not matter.
yeah, but we have a directional, so we care.
But a directional, it basically is your life or death. Um,
Yeah, so I guess I'm drawing like what the radiation pattern on top of the angle. So like you would expect to be sending this much power, but in reality for this case, you'd be sending like something around here. And you have to make sure that
oh,
this amount is enough for the ground station to do, right? If you're
yeah.
at if you're pointed like, a little bit too far off, then like, hypothetically if you were pointed off here, this would not be like anywhere near enough power. You would have to be like within a certain amount, and that's something you can find from usually from the data sheet.
Yeah. Also, let me. I did just check again just to make sure. Uh, Technically, what I said was true, but it's actually the link margin that's in reference to.
Into where like
Like link margin is basically just the concept of the difference between like expected power and then expected power received at the receiver's end and then the receiver sensitivity. So basically, can your receiver receive enough power to actually process the information? And they want it to be 6 decibels there.
okay,
Yeah.
all right, so yeah, it's a margin of error between.
It's a margin of error.
Okay.
Obviously anything better is better. But 6 decibels is what they say. Now, you do have other things you have to consider as well with your link budget. Obviously, the most notable one is thermal noise because thermal noise, higher it gets, basically the worse your system actually becomes from sending data. Another thing you have to consider is modulations because modulations require more energy to like process the same amount of bits. So because of that, something as high like something very complicated as KPSK is going to require more energy, which effectively reduces how much transmission power you have and effectively reduces your link budget accordingly. So you have to make sure to consider those design decisions. You also have to make sure to consider your error rates because your error rates are something that you want to ensure. If you don't care about losing that many bits or like having a bit flip every 1,000 bits sent, then that means you can just send it without having to actually worry about like the errors of your bits. So you can just send it as much energy as possible. But it consumes more energy just to basically correct for those error rates and ensure that the signal sends confidently.
Okay.
Yeah.
So like bit flips that happen in between transmission and receiving.
Yeah.
Or okay.
And just because you do a link budget for a downlink, you also have to do a link budget for your uplink as well.
Yeah, and for us that matters because we're not uplinking, just commands. We're uplinking entire control algorithms. A bit flip in, an algorithm could be the difference between it being stable versus unstable. So
Yeah. Let's see what else. So data array is obviously the biggest one, in terms of just overall energy consumption because you do want to make sure that your data rate is at a friendly data rate that both gets your system requirements done in time, but then also make sure that you don't overburn your system with more energy. That's more something the electrical side has to deal with personally in terms of power, but it is something that a lot of people are going to ask you questions on later
yeah.
because they do.
They know we have weaknesses.
They know they know we have weaknesses in our system.
Yeah.
My biggest weakness is my system does not work.
Right.
Nah.
I mean,
So
you work at it, right? I think you
you
make
work at
progress.
it constantly. I think one of the most obvious things, eventually, I hope it doesn't come to it, but like you're going to have to constantly change your link budget accordingly. But eventually, I hope like you don't have to scrap it, because that's probably one of the worst things to do.
This is something I think this is why you have James working on automating the link budget.
Yeah, because like also, yeah, one other thing about the link budget. So the link budget does also have a good variation in regards to different positioning in space. So because of that, a lot of your values do change over the parameters of time because one of the most notable ones is altitude. Obviously, the closer you are in space, or the closer you are from like your ground station to your cube satellite, you are able to basically confidently have better solutions for communicating. However, yeah,
Yeah, this happens.
yeah.
Yeah,
So
atmospheric losses will decay your orbit slowly but surely, and this is, I think, this is gonna happen. I think this like the full scale of this conversation is gonna happen when I talk with Sarah in program management, because this is an important part of ConOps is planning for how long the mission will last,
yeah,
and communications is affected by that because an altitude of 350 kilometers is way different than like 300 kilometers. Like a 50-kilometer difference in the distance traveled is it is a difference, right?
it is very much so.
Yeah.
Um, Overall, the link budget is basically your bread of comms. If you don't have that many answers on what you want to like do with your transceiver or patch, the link budget pretty much forces you to think of it because every decision you make is a calculation on the actual link budget probably. And so like what I mean by that is like when you're trying to calculate for something like noise temperature, you will like have to make sure like, oh wow, we have to optimize for noise temperature. And we also have to design to make sure our ground station is like going to be at an optimal time and temperature as well for your system. Otherwise, this is shit.
Yeah. Yeah. Actually, one thing that will have to be planned eventually is, I guess, or I say planned, but what I really mean is like considered is the slewing of our satellite as we go pass over a ground station. So, in the sense of you are tracking a ground station, we do have a small disturbance going on that is 2 to 20% of the control torque. We want to maintain like this angle as small as possible, but we have like an active thing on our satellite disturbing it from that. And so maintaining that is important, especially from a comms perspective, because like pointing losses, I think pointing losses are the major source. So yeah.
Pretty much. Yeah.
You gotta maintain this angle. There's a little control problem going on in here. But yeah.
It'd be a shame if we put something on our satellite to make that controllable.
Yeah, it'd be a real shame. All right. Yeah, but that's a concern that'll come later. I think this is. Should I share the video? I kind of want to.
Of
The that software I wrote, the one with the pointing, like that's what that was meant to address, but I never got to finish it because we had other priorities. Yeah, you know what? I'll share it. But one of the things that I did for this, which was actually like I think Shri, I'm pretty sure you helped with this. Actually, no, I
Yeah.
know you helped with this.
Yeah.
If you're on my YouTube, you should already know that I made this, but this is meant to be like the tracking of a ground station, and then I think this angle is a bit thinner than it should be. I think I was assuming like less like 5 degrees or something, or some like it was stupidly small, but that on like a satellite that is tracking a ground station, this thing doesn't have the fluid disturbance on it, but it is entirely possible for like there to be a problem. Like in here, the satellite is not able to track it well enough to maintain the link that we expected it to. So there's actually a disconnect here between the antenna and the ground station. So things like this are like there is something to consider, not necessarily right now, but it will be important soon, very soon.
Mhm.
End of phase A type of soon, end of 6 months type of soon. But yeah.
Yeah.
All right, let's see. And then the very last thing is the simulated communication test.
So, okay.
A quick-
Obviously, I have not gone through that much of the actual test itself. Other than I think I did read a little bit of it, so I am aware of how it's supposed to work. So what you have is a flat set, and then you have your communication system on it. So transceiver and antenna. What you do is you basically demonstrate to them that you can send packets to an available ground station. Now, this ground station has to be a mile away, but what that means is inherently you could have your own antenna or your own ground station as well. Or what happens is you just have to demonstrate with whatever receiver possible that, oh, we can send these packets. We have our modulation set, our packet decoding and encoding set, our encryption layer set for our system. And then overall, we can guarantee effectively that all of our data and algorithms are generally are passable. Now, the way they set it up is obviously you need the flat set. And then the main issue I believe we'll probably have personally over this project if we do go into phase B is someone's going to have to develop an antenna for that. So ironically I actually did prepare for this.
Oh,
Yeah, so I have one of my members currently working on building an antenna.
damn.
Yeah, I did prepare for the scenario because what happened is with cube satellites, testing is one of the most difficult parts with communications because effectively speaking, if you're operating in something along the lines of S-band, you don't have any relative communication receiver. So when you test it, it's a bit difficult as opposed to like an amateur radio system where like, oh, I can just send it to like my friend who also has one, or like to the community that oftentimes is very supportive. So instead, you're going to have to work on building one. So right now I have David working on that, and David is very skilled in terms of applying physics to actual practical means. So he has come up with an S-band patch antenna, and what we could do is we can try to hook that up into a computer system so we can have a software-defined radio that just has an antenna attached to it, and then accordingly we can just pretty much do all of our operations like that.
And we would just need to deploy like the antenna at one location and then simulate some like a receiver type of ground station at like a mile-ish away.
Affirmative.
And then
Yeah, something along the lines of that. Now, obviously, what I'm more afraid of is once again the directional loss because you basically are going to have pretty much as precise computer vision. Um, I know it sounds weird, but you guys have seen Linus Tech Tips.
Yeah.
So in one of their videos, they actually had a similar problem to this, where they're trying to basically share a network with like another building that didn't have access to a network. So what they did was they took two antennas and they basically relayed like their communications for like basically sending over files to like the different building by just straight through an antenna system. So they built an antenna on top of one rooftop and another antenna on the another one, and then they were just aligning it. They're just lining up the antennas so that they match like the specific orientation to each other. The connection worked, and similarly, this is what we're gonna have to do for phase B. So it's definitely doable. Now, granted, they had both a company expertise in terms of they had thousands of dollars, or not thousands, hundreds of thousands, and just to pay on labor to do this.
They had a
Um,
dedicated staff and budget. We
they,
have
yeah, we have
un-
barely any.
we have undergrads.
We have undergrads, but that's the best labor. I
It's completely free and they're willing to do it. I'm
They're-
so sad I was one of them. I still am.
Yeah, but I will say it's definitely doable, so I don't have any hesitations there. What what's going to happen is someone's going to have an electrical engineering background with coding skills as well, because the software-defined radio is one of the hardest parts of the entire system.
Hmm. Yeah.
Now, that is roughly as far as I went in regards to the actual flat set testing and also the phase B testing as well. Personally speaking, I don't know where the direction is going to be in the future, and that is probably up to whoever's the lead at that time to decide.
You say it like it's a mystery. It's probably James. No, it
Oh
is.
yeah,
It
no,
is
no,
James.
no. I know it's James, but it doesn't mean necessarily speaking that in case we ever have to do like future projects or do anything that happens along the way, like where James is not like the lead. Like obviously, like I'm saying this in reference to like if there's like any like other communication lead in the future.
Okay. Yeah, yeah. He has to pass the torch on. Um.
Yeah, yeah.
All right. Yeah. So.
And then obviously, like I think is the phase B testing also just happens afterwards too. Anyways,
Yeah.
like it's like a year after or a year or two after, so it's not like it's not like right then and there. So like it is always like
Yes.
way beyond
So.
either of our time.
Yeah. So. Spencer, Spencer, I think I told you this already, but like the current plan is to have what unit testing is done by like August, and then subsystem should be done by, I think we plan like December, and then system level testing should be done by like next June. But this
Next
is like like this already is like a really hard goal for us because of like the procurement delays. But yeah,
Yeah.
this is roughly like this is like the ideal timeline that we would like to have. But and then like immediately after this is where like your 5 tests are, and one of those is like this communication test.
Mm-hmm.
And then you hand it off to UNP, the Air Force, and they'll do some more tests and then put on a rocket for you. But it'll be a process. And this is one of those tests that will have to happen.
Yep.
All right.
Is that all?
I think so. Spencer, do you have any questions?
Real quick, I was gonna ask, like, if we get SDK to work and SDK can generate a link budget for us, like, where does that fall into?
SDK's link budget, I still have some issues with it. No, I know, I'm aware. I'm still a little bit concerned because their systems are like more positional, and like obviously they can generate like data time windows and all, which is nice. I still appreciate that information. But inherently they don't actually consider any other losses like line loss, pointing loss, because their pointing system's not that accurate in comparison. It's just like, is it there or is it not there? It's not like, oh, like I get the actual direct signal accordingly.
Yeah.
And then also temperature loss as well, because those are things you have to consider.
Mm-hmm. There's a lot of losses, and I guess if the simulations team is ever revived, like with SDK as like, you know, one of the things that we're working on, one thing that I think we should do is incorporate the SDK like environment with James's like budget like calculator.
Yeah.
Because, you know, if we can just be like, okay, you know, every like once a second calculate the link budget, like, and then, you know, we just simulate a situation or a scenario, right? We just say, okay, try pointing at the ground station. You know, we have like an actual physics for the attitude, determination, and control. You know, we keep track of the temperature at this using, you know, some thermal analysis. and then we incorporate all that into a link budget, like that would be very helpful for us to like, you know,
Mhm.
better plan our mission. And yeah,
Okay.
unfortunately we
Yeah.
we can't work on that right now. So yeah, limited manpower, the wonders of it.
Yeah.
All right, I think
I think
that's
we're done.
yeah, I think we're done.
Are we done?
Yeah, we're
I'm
done.
gonna-
Oh.
Yeah.